Hi class, this is Sir Alex Basco and welcome to our lesson in General Chemistry 1. Today we are going to discuss lesson 7, which is all about gas laws. Today what we are going to understand is first to understand what pressure is and how it relates to gas, as well as the various laws that govern gas behavior. So let's first look at our goals. First is for you guys to be able to define the pressure and what pressure is, and give some common units of pressure. When we are talking about gas, we usually talk about it in pressure, and today we are going to learn what atmospheric pressure is, as well as what are some of the units that we use to measure pressure. Also, be able to use gas laws to determine pressure, volume, temperature, or number of moles of gas. So we'll be doing some computations today to measure pressure, volume, temperature, or number of moles of a gas using various gas laws. Next, the last one is to use the ideal gas equation. And where did we get the ideal gas equation? We will learn today to also calculate pressure, volume, temperature, or number of moles of a gas. So let's begin first by discussing what pressure of a gas is. Pressure is basically a measurement of force, and it is a measurement of force that it is applied on a surface, more specifically relative to an area of a surface. So one thing or two things that I want you guys to remember about pressure, it's a force divided by a certain area. What that means is how much pressure is being applied to a certain area. So for example, you have a piece of wood right here, and this piece of wood is constantly exerting a force onto this surface right here. And how much of this wood exerts on this surface right here is determined by how much area basically is in contact with that force. So if you look at this piece of wood right here, this piece of wood has a certain area, and that's basically how much area is being pressured or is being forced onto this piece of like blue metal. So pressure, if you look at this is basically force over a certain area. But when we talk about gas, it's basically the same concept. But when we talk about atmospheric pressure or pressure exerted by the gas, it is the force exerted by the atmosphere. So instead of a piece of wood, something like this, we have the atmosphere that is exerting a force onto a certain area of a surface. And this atmospheric pressure is dependent, or its value can change depending on the location, temperature, and weather conditions. What I want you guys to think about in when we talk about atmospheric pressure is because of the gravity of the earth, basically we are living in a sea of gas. What I mean by sea of gas, everything that surrounds you is basically gas molecules, and we are continuously being experiencing actually a certain pressure of gas called the atmospheric pressure, and that atmospheric pressure is actually equal to 1 atmosphere, which is a unit of pressure, or 1 atm. So you can think of it this way. So let me draw. So this is the world, right? And during the creation of the world, or let's just think of, let's simplify it. So this is the earth. So we have earth right here, and because of the massive size of the earth, it has a gravity, and because of that gravity, various molecules of gas stays on the surface of the earth instead of going out into the space. Without this gravity on the earth, the atmosphere that is present on the surface of the earth will actually flow out of the earth. But we know because of gravity, we have a copious amount, or we have a lot of various gas molecules that is found on the surface of the earth. And most of that, if we are going to look at the atmospheric composition of the earth, is nitrogen. Next we have oxygen, and then carbon dioxide, and then the various minuscule other gases. So All of that is can be found on the surface of the earth, and oxygen is the one that we continuously breathe, and we experience this amount of, or this amount of various atmosphere or gas molecules that you found on the surface of the earth. They actually have weight, and if something has weight, it can exert a pressure. So if you are standing on the surface of the earth, so let's say this is you, so this is you right here, you would actually experience a pressure while standing on the surface of the earth, and that pressure is usually we denote it as 1 atmospheric pressure. We'll learn more on that later. So I want you guys to look at this ball of balloon here. We know we can inflate balloon, right? So if we have a balloon, so if we draw something like this and it is not inflated, the reason that it's not inflated is because there's no gas inside that pushes it out to expand. But if we have a certain amount of air that we push into the balloon, what happens is that the balloon can start to grow, right? It's increasing in sizes. The reason that it increases in sizes is that the air molecules, so these are air molecules right here, that is being pumped inside the balloon is basically causing a pressure. It's pushing onto the surface inside the balloon, causing it to expand. And this force is much greater than the force that the balloon is experiencing surrounding it, because everything outside of this balloon is experiencing also an atmospheric pressure. So certain 1 atmospheric pressure. And the reason that the balloon expands, it's because the pressure that you're basically pushing inside the air, this pressure is much higher than the pressure on the surface, or on the pressure that the balloon is experiencing outside, causing it to expand. So the pressure here is much higher than the pressure from the outside. But once when you stop blowing inside the balloon, what happens? The same situation like this, it's not expanding anymore, right? What happens is that the pressure here is actually equal to the pressure there. So the pressure of these air particles that causes these balloon to have this shape, it's pushing it outside instead of shrinking it, is this pressure here is equal to the pressure of the surrounding atmosphere that keeps pushing onto the balloon for it to shrink. And when these two pressures are equal, now you have this constant circumference or constant shape of your balloon. So that's what basically atmospheric pressure is. Because of the various atmospheric or gas molecules that is found on the surface of the earth, because of gravity, they do not flow into the galaxy or into the space. These gas particles has mass, and when something has mass, it can exert a pressure onto you. And when we have these small particles with minuscule mass gathered up together, we have tons of them, we can actually experience a pressure, and we call that 1 atmospheric pressure. So that's basically what pressure of gas is. And atmospheric pressure is just the standard units of measurement that we use, but there are other units of pressure that we use. One of them, oh, here you go. So the standard pressure is, let me just erase this. The standard pressure is equal to 760 milliliters of mercury, which is equals to 1 atmospheric pressure, which is equals to 14.7 pounds per inches squared, or pounds per square inch. So these are the various measurement that we can use to talk about pressure. And I want you guys to particularly look at this. Pounds is a unit of force, same with Newton. An inch is a unit of a area of a surface. An area if you guys remember. So if you have an area, let's say a rectangle, that's length times width. So if this is meter, this is meter, that will give you meter squared. But if this is inches, this is another inches, that would give you inches squared. So this is an example of a force over area type of measurement. And since pounds is a weight, and weight is actually a measurement of force, therefore pounds per square inch is actually a unit of pressure. So these are values that are very important, and I want you guys to remember. 760 millimeters milliliters of mercury, which is equals to 1 atmospheric pressure, which is equals to 14.7 pounds per square inch. And these values is basically the pressure that you are experiencing right now. Wherever you are on the surface of the earth at sea level, this is the pressure that these bunch of molecules, air molecules we have on the surface of the earth is expressing on you. So if you look at your skin right now, your skin is actually experiencing a pressure of 1 atmospheric pressure. But we cannot feel it now, right? It's because we've basically used to it. And of course, there's other explanation, but I'm not going to go deep into that explanation. But I hope it's clear by now what atmospheric pressure is. Now let's look at this table right here, which are the units of pressure. We have units of atmosphere. We have units of Pascal, kilopascal, millimeters of mercury, torr, pounds per square inch, and bar. So these variety of units has a specific number or a specific measurement, and in a standardized atmospheric pressure at sea level at 0 degrees, this atmosphere is equals to 1 atmosphere, and all of these are equal. Okay, I want you guys to remember these, more specifically atmospheric, millimeters of mercury, and pounds per square inch. 1 atmosphere is equals to 1.01325 times 10 to the 5th Pascal, which is equals to 101.325 kilopascal. And this is also equal to 760 millimeters of mercury, which is equals to 760 torr, which is equals to 14.7 psi, which is pounds per square inch, or you can write it this way, and this is equals to 1.01325 bar. So all of these are basically the same or equivalent in value. They're only different, it's because we're using different types of units to measure them. For example, you can think of this as centimeter, and this is inches. So they are different units, but you can find an equivalent value with them. Having said that, what I want you guys to know now is to be able to convert one unit from the other. So for example, if I were given an atmosphere, what I want you to be able to do is use that atmosphere and be able to convert it, let's say, to millimeters of mercury. Or if I were given millimeters of mercury, be able to take that value of millimeters of mercury and convert it to, let's say, pounds per square inch. So that's what we're going to do in this sample problem. So the barometer in Manila gives a reading of 0.95 atmosphere. What is the equivalent pressure in A, torr, and B, pounds per square inch? So let's try and solve this. We are given, so let's write our given. So first given is we are given a pressure in atmosphere. So we are given a pressure of gas in the atmosphere, which is equals to 0.95 atmosphere. And it's asking, what is this atmosphere equivalent in first, torr, and B, pounds per square inch. So how are we going to do that? Solution. In order for you to do this is just basically conversion of units. This is where the table that I showed you earlier will be helpful for you in solving this. So for first, if I'm looking for the pressure in torr, or the pressure of atmosphere in units of torr, what I'm gonna do is I'm gonna take the units given to me, which is 0.95 atmosphere, and know that this 0.95 atmosphere is actually equal to, in every 1 atmosphere, is equals to 760 torr. And that 760 torr is actually equal to, so the atmosphere gets cancelled, that is equals to 722.00 torr. So that's how you can convert it. So basically, take your given value and multiply it with the conversion factor, which is an equivalent value between the two units that you are looking for. So let's say we have a pressure, or we are looking for the pressure of atmosphere in units psi, or pounds per square inch. So take this value that we're given to you, 0.95 atmosphere, and multiply that with a conversion factor, or when I mean conversion factor, is the equivalent value between the value given to you and the value that you're looking for. In 1 atm, how much is that in pounds per square inch? We just looked at earlier, we know that this is equals to 14.7 pounds per square inch. And make this into your conversion value, which is you're gonna place the units that you're canceling at the bottom, so that gets cancelled, and take the units that you're looking for on the numerator, psi. So that's 0.95 multiplied by 14.7 psi, and that is actually equal to 13.97 pounds per square inch. So this is just conversion, converting values. So for example, it's similar with how you would convert centimeter to millimeters, kilograms to grams, etc. You just have to find the conversion factor. So now that's all about the units of pressure. Now let's talk about the various gas laws. So these gas laws are laws in which helps us explain the behavior of gas in relation to volume, pressure, the temperature, and the number of moles of gas. So because the behavior of gas is affected by pressure, by volume, temperature, and the amount of gas in terms of moles, which we use the letter N to denote the moles of gas. Then by using gas law, we can actually find the relationship of these four. So the first gas law that we are going to talk about is called Boyle's law. Boyle's law states that under constant temperature and amount of gas, the volume of any amount of gas is inversely proportional to the pressure exerted on it. So what do we mean by that is, let's look at the picture right here. So according to Boyle's law, the volume of any amount of gas is inversely proportional to the pressure exerted on it. We can write this in the equation V is proportional to 1 over P. This V is proportional to 1, is directly proportional to 1 over P. This is what we call an inverse proportion. What do we mean by inverse proportion? Every time in inverse proportion, what happens is that every time your pressure increases, your volume decreases. That's what inverse proportion is. So when volume increase, pressure decreases. Or when volume decrease, pressure increases. So their direction is opposite. That's what we call inversely proportional. And if we look at this right here, every time we lessen the volume, so this is your volume right here, you go from 4 to 2, you notice that the pressure increases. but every time the volume goes up, the pressure decreases. So that is the inverse relationship between volume and pressure. So that is Boyle's law. There is a inverse proportion between the volume and the pressure of gas. So then we can relate it if we have an initial condition of gas and then another final condition of gas. So if we have a situation where we have an initial and a final conditions, meaning we have V1 and P1. So the initial meaning the first values of your volume and the first values of your P. And then for final, we have the final volume of the gas and the final pressure of the gas. We can actually find a relationship between this initial and final conditions using the inverse relationship or the Boyle's law. So that is this right here. So the product of your initial volume and initial pressure should always be equal to the product of your final volume and your final pressure. And we got this from the inverse square law. We know that V is inversely proportional to 1 over P, or we can just change this to 1 over P. If we get this right here, these are initial values, and we know this should also be the case to our final values, or our final volume should also be inversely proportional to the final pressure. Then rearranging these equations, you would get V1 P1 is equals to 1, and same here, V2 multiplied by P2 is equals to 1. And since this is actually some form type of constant, we just write 1, but since we have constant temperature and constant N, meaning this values right here does not actually change, it's constant, hence we can equate this two, and that's how we get P1 V1 is equals to P2 V2. So this is a Boyle's law. This is something that I want you guys to remember. The product of the initial values of pressure and volume will always be equal to the product of the final pressure and final volume. So let's take this as an example. The pressure exerted by a gas sample in a 500 ml container is 1.35 atmosphere. What pressure will the same amount of gas exert if the volume is decreased to 196 millimeters or milliliters, while the temperature is held constant? So let's write our given. So first, the pressure exerted by gas sample in a 500 ml container. So this 500 ml container right here is our first volume. So because volume ml is a units of volume, so that's 500 ml. So we started with the 500 ml sample of gas, and the pressure exerted by this amount of gas, this volume of gas, is equals to 1.35 atmosphere. So your P1 is equals to 1.35 atmosphere. What happens then? What will be the pressure if the same amount of gas, meaning our N is constant, same amount of gas, constant N, if the volume is decreased? So they give us a second volume. If we take this 500 ml and change it to 196 ml. So basically, if you have a container, and this is a 500 ml container, and it has this amount of gas, you can think of it that way. This gas is has a pressure of 135 atmosphere. What if I take all of this gas and move it into a much smaller container? the same amount still. And this is 196 ml. So what it's asking me is what pressure will the same amount of gas if the volume is decreased. So what will be the new pressure? So what will be P2? And the formula we know, this is Boyle's law, because temperature is held constant T. If you have constant N and constant T, constant number of moles and constant temperature, and we have initial volume and pressure, and we have initial or final volume and pressure, we know that this is Boyle's law. So P1V1 is equals to P2V2. So the solution is, we're going to take this equation right here, P1V1 is equals to P2V2. And then we're going to separate P2, or basically rearrange this equation so that we are solving for P2, because we are looking for P2. So that's basically dividing both sides by V2. So P1V1 divided by V2. So just take your values and plug it on your equation. Or in P1 is equals to 1.35 atmosphere multiplied by V1, which is 500 ml, and then divided by that to your new volume, which is 196 ml. So the ml gets cancelled. You're left with atmosphere, which what you are looking for, and this is actually equals to 3.44 atmosphere. And let's check if that makes sense. We know that in Boyle's law, the volume should be inversely proportional, meaning if my volume decreases, my volume or my pressure should increase. And looking at this right here, we know that our volume decreases. Now let's look at our pressure. We know that our pressure now is 3.44, and we can see that our pressure increases. So it follows the Boyle's law. So this is how you use Boyle's law in order to solve for basically initial or final pressure and volume. It's a relationship of gas in terms of pressure and volume. Just remember that the temperature and the number of moles is constant. Now let's look at the second gas law, called the Charles law. Charles law is the volume of gas. It states that the volume of gas is directly proportional to its absolute temperature under constant pressure and the amount of gases. So what do we mean by that is that V is directly proportional to T. What do we mean is that if our volume increases, there should also be an increase in temperature. Or if our volume decreases, our temperature should also decrease, provided that our pressure and the number of moles of gas we have is constant. And if we look at this moving picture right here, you can see that as your volume decreases, your temperature also decreases. But if your volume increases, your temperature also increases. So it has a relationship that is basically x is equals to y right here. So if I increase my temperature, my volume also increases. If I decrease my temperature, my volume also increases. This is Charles' law. And similar with Boyle's law, we can create a condition where we have initial and final conditions. Here we would see that we would have the quotient or V1 divided by T1 should always be equal to V2 divided by T2. or the quotient of the initial volume and temperature should always be equal to the quotient of the final volume and temperature. And rearranging this, we can get another equation that is quite similar in the first one, but this time it's the product of the initial volume multiplied if the product of the initial volume and the final temperature should always be equal to the product of the final volume and initial temperature. And we got this from here. We know that V is equals to T right there, right? So, and then some form type of constant, because we have constant P and constant N. So if we have our V1 and T1, and then we have our V2 should also be equal to this right here. You have your K constant. So V1 over T1 is equals to K, which is also equals to T2 or V2 divided by T2. So that's basically how we got this equation right there. But one thing that I want you guys to remember is, since we are dealing with temperature, temperature must always be in Kelvin. And in order for you to measure Kelvin, if you are given degrees of Celsius, you just have to add 273.15 to get Kelvin. So let's solve for this sample problem. A 300 ml sample of gas at 125 degrees Celsius is heated to 155 degrees Celsius. What is its final volume when the pressure is held constant? Okay, so let's write our given. We are given our V or our V1. We have our V1, which is 300 ml, and then this 300 milliliters of gas is at 125 degrees Celsius. So the temperature is 125 degrees Celsius. What if I heated my gas from 125 degrees Celsius to a new temperature of, or to a final temperature of 155 degrees Celsius? What it's asking is what would be its final volume. So we just discussed the formula earlier. The formula we know is the initial volume multiplied by the final temperature should be equal to the final volume multiplied by the initial temperature. Solution. So we'll take our equation V1 T2 is equals to V2 T1, and since we're looking for V2, we'll just have to arrange this so that V2 is once on one side and the rest is on the other side. So that is V1 T2 divided by T1. So finding the value of V2, you just have to plug in your values, or in your initial volume of 300 ml multiplied by the final temperature, which is 155 degrees Celsius. But this time you have to change 155 Celsius to Kelvin. So you have to change your temperature to Kelvin. So that's 155 degrees Celsius plus 273.15, which is equals to 398, 428.15 Kelvin. The same thing, you have your 125 degrees Celsius plus 273.15, or that is equivalent to 398.15 Kelvin. So your 155 is now 428.15 Kelvin. And lastly, multiply that from your original temperature, which is 398.15 Kelvin. plug that on your calculator, you would get that the original or that the final volume is equal to 322.60 ml. And if you're going to check that, we know that in Charles' law, V is directly proportional to T. If we look at this right here, so we have our T and our original V. So we have our 3 ml to our 125 degrees Celsius. And if we compare it, we change our temperature of 125 to 155 degrees Celsius. So now, what is our new ml? That is 322.60 ml. So we have an increase in both. So the Charles law is applied because it should have, because this is the behavior of gas. As long as pressure N is held constant, and the number of moles as well, N is also constant. Okay, I hope that's clear. So that is Charles' law. Lastly, let's talk about Avogadro's law. Avogadro's law states that under constant pressure and constant temperature, the number of moles of a particular gas sample is directly proportional to the volume of the gas. So again, this is direct proportional. It's the same with Charles' law, or in our volume and our temperature are directly proportional, and it is also the same for volume and the number of moles of gases. So using the same equation that we have, we will get the product of the original volume and the final number of moles should be equal to the final volume multiplied by the original or initial number of moles of gas. Next, let's talk about lastly, which is an important aspect of the behavior of gas, called the ideal gas law. Ideal gas law happens when we combine Boyle's law, Charles' law, and Avogadro's law. This is a simplification. Ideal gas law is basically a combination of various laws, more specifically Boyle's law, Charles' law, Gay-Lussac's law, and Avogadro's law. But Charles' law and Gay-Lussac's law is actually it's similar. It's just in different direction, but it's similar. But overall, when we combine all these three gas laws that we discussed, Boyle's law, Charles' law, and Avogadro's number, we would get a new equation called the ideal gas equation, which is PV is equals to nRT. P is pressure, V is volume, and PV is equals to the number of mole multiplied by R multiplied by T. And R is what we call a universal gas constant. R is constant, okay? It doesn't change. And the value of R is 0.081 liters atmosphere per molar or moles Kelvin. So this is actually just one value of R. There are various values of R depending on the units, but they are all the same equivalent value. It's just maybe the number is not the same, but the units is different. For all intents and purposes, for most of the time, we are going to stick with this value of R, unless it's stated in the problem. In that situation, what you need to remember is to be consistent with your units. If you use R, make sure you are using liters for your volume, you are using atmosphere for your pressure, moles for your N, and Kelvin for your temperature. You have to be consistent. Otherwise, your value or your answer will be very, very different. Again, you have to be consistent with the units that you are going to use. Again, this is the R that we are going to use. There are different values of R, although they are all the same or equal values. It's just the number, the magnitude may be different, and the units, it's because we changed the units. But again, for all intents and purposes, we are sticking with our R unless stated in the problem. So this is the summary of all the gas law that we talk about. We have Boyle's law. Boyle's law has a constant temperature and N, wherein the volume is inversely proportional to P. And we get these values right here if we have initial and final conditions. For Charles' law, we have constant pressure and N, and the volume is directly proportional to the T. So increase in volume is increase in temperature. And this is if we have initial and final volume. So the product of your initial volume and final volume is equals to the product of your final volume and initial temperature. The same is true for Avogadro's law, where we have a constant pressure and temperature, where volume is always directly proportional to N. Increase in the number of moles equals increase in the volume. And we use this equation. And lastly, combination of these three laws, we have ideal gas law, that in under standard conditions we have this equation. And one way for me to remember this equation, I just say PERV-NERT, PV-NRT, PERV-NERT. That's how I remember this equation. Now let's take these sample problems. 5 moles of H2 gas were collected at a pressure of 0.98 atmosphere at 27 degrees Celsius. What is the volume in liters of the H2 gas? So let's write our given. We are given 5 moles of H2, hydrogen gas, were collected, and this 5 moles of H2 gas has a pressure of 0. So this is your N. Let me rewrite that. You have your N, which is equals to 5 moles of H2. You are given your pressure, which is equals to 0.98 atmosphere, and we are given a temperature of 27 degrees Celsius. That is being asked, what is the volume in liters in terms of liters? Of the H2 gas. So the formula that we are going to use is the PERV-NERT, or the ideal gas law. That is because that is the relationship between all these values given to you. Solution. The first thing that you have to understand is your R is what? 0.0821, right? Your R is 0.0821 liters atmosphere per mole Kelvin, which means we have to use liters, atmosphere, molar, and Kelvin. So we have our mole, we have our atmosphere, but our temperature is in Celsius. We have to add it in Kelvin. So we have to change temperature from degrees Celsius to Kelvin. So that is actually 27 degrees Celsius plus 273.15. That is equal to 300. Yeah, that's 300.15 Kelvin. So solution, we use this equation right here, our PERV-NERT, and what we're looking for is V. So we have to rearrange this equation so one side is V and everything else is on the other side. So that's V is equals to nRT divided by P. So V is equals to, let's plug in your values. You have 5 moles multiplied by our R, which is 0.0821 liters atmosphere per molar Kelvin, and multiply that for temperature, which is in units Kelvin, 3.15 Kelvin. All of that divided by pressure, which is 0.98 atmosphere. So the moles gets cancelled, your K gets cancelled, and the atmospheres get cancelled. Just plugging that out on your calculator, you would get that the number of volume is equivalent to 125.73 liters of H2. That's how you solve sample problem, or that's how you solve ideal gas problem. Let's take this sample problem 7.5. How many moles are present in a gas that has a volume of 970.5 millimeters at 24 degrees Celsius and 600 millimeters of mercury? So let's write our given. We are given a volume of 970.5 ml. We are given a temperature of 24 degrees Celsius, and we are given a pressure of 650 millimeters of mercury. What it's asking is how many moles is present in our gas. What is our N in terms of moles? Formula again is just our per nert right here. Okay, so again, your R is in values of liters, atmospheres, molars, and Kelvin. So we have to change this to liters. So for solution, you have to correct your units. So 7 for our volume, so that's 970.5 ml. What we have to do is in every 1000 ml there is 1 liters. So that's 170.5 ml divided by divided by 1 or divided times 1 divided by 1000, that is equals to 0.975 liters. For temperature, we have 24 degrees Celsius plus 273.15, that is equals to that is equals to 297.15 Kelvin. And lastly, for pressure, 650 millimeters of mercury. You just have to change this in atmosphere. We know that in 1 atmosphere there are 760 mmHg. Cancel the mmHg, and this will give you a atmosphere of 0.8553 atmosphere. So that is the first one. Next, we can now solve for N. We know that per nert is equals to nRT. So that's N is equals to PV divided by RT. N is equals to our pressure, which is 0.8553 atmosphere, multiplied by volume, and our volume is 0.9075 liters, and our R is equals to 0.0821 liters atmosphere mole Kelvin. And we have to take that and multiply it by temperature, which is 297.15 Kelvin. So the Kelvin gets cancelled, liters get cancelled, atmosphere gets cancelled, we are left with mole. And the number of moles we have is equals to 0.03 moles of gas. So I hope it's easy. That's how you solve ideal gas law. If you guys have any question, do not hesitate to message me. Thank you so much, guys, and may you guys have a great day. Thank you.